The agenda for today is to discuss a nice relationship between regular languages and special kinds of subset of natural numbers. We shall see a necessary condition for regular languages in terms of natural numbers, and the result that we are going to discuss today is about ultimate periodicity. We shall see when a subset of natural numbers is said to be ultimately periodic. We can start with this example. Consider this subset of natural numbers. This is the notation for natural numbers including 0. If you look at this set, you can see that after the element 19, it is a periodic set with period 3. That is, it contains every third element in the set of natural numbers from 20. 20 is there, then after that every third element is there, 23, 26, 29. So you can see that it is ultimately, after this, it is a periodic set with a period 3, and that is what it is called, ultimately periodic. Not initially, but ultimately it is a periodic set. A set which is periodic after a finite prefix like this is the finite prefix. After that it is ultimately periodic, it is periodic. Such a set is called an ultimately periodic set. Formally, you can define an ultimately periodic set as follows. A set U is called ultimately periodic if there exists two natural numbers, n greater than or equal to 0 and p greater than 0, such that for all elements m in the sequence, m plus p is also in the sequence. That is, if you look at any element after the prefix, m is in the set if and only if m plus p is in the set. For example, here you can take n as 20 for any value greater than or equal to n. Okay. So, any value greater than or equal to 20, you can see that m is in the set if and only if m plus p is in the set. If you look at any element, for example 38 as m, you can see that m plus 3 is there. So, if m is there, then m plus 3 is there. And why 38 is here? Because it is 35 plus 3, that is if and only if, you can easily verify. So, that is the formal definition. And here the number p which you are adding to m, like here it is 3, is called the period of the ultimately periodic set U. For an ultimately periodic set U, neither n nor p may be unique. For example, here you have n as 20 and p as 3, that you already verified. You can also take n as 21 and p as 6. You can see that for every value greater than or equal to 21, say 23, 23 is there if and only if 23 plus 6, 29 is there. So, that sequence is again there. So, n and p may not be unique. I hope you are getting me. And we can see that regular languages over singleton alphabet sets. If you look at regular languages which are defined over singleton alphabet set, just one alphabet, then you can see that such languages and ultimately periodic sets are strongly related. And later we can see what that strong relation is. So ultimately periodic sets and regular languages, we can have a theorem which has got a very important application that we will see today, and the theorem is saying if L is a singleton alphabet language, so if L is a language over a singleton alphabet set, just one alphabet, here it is A, but it doesn't matter what that alphabet is. So what is important is if you look at a language over a singleton alphabet set, then the theorem says the language is regular if and only if the set of string lengths in the language, the set of all m such that a to the power m is in the language, meaning this is the set of all lengths of the strings in the language, is an ultimately periodic set. So it is a very strong claim. If you look at a single alphabet language, the language is regular if and only if its length set is ultimately periodic. Later we can see examples. Now we can try to look at a proof outline. First, for only if, we have to prove it that if and only if case we will see later. Now we are going to look at a proof idea for only if. The complete proof is not going to be given, but not difficult. So we have to prove only if, that is it is regular only if the length set is ultimately periodic. Now suppose that a language over a singleton alphabet set is regular, then without loss of generality there exists a deterministic finite state automata accepting the language. See that the language is over the singleton alphabet set. So in the Dfa, transitions are all for the simple A, because only A is the simple. So if you look at the Dfa, what will be it? You need to have a transition for A, and from here again for A, same for this state as well. So always you need to have a transition for A. And now suppose the language is infinite, that is there are infinitely many strings, then you can easily observe that there must be a loop like this, then only it can accept infinitely many strings. And in the loop as well, each edge is for the simple A. So if there are I edges here, then it is A raised to I, the string which is taking back. So I hope you are getting me. So you can generally represent such a Dfa like a lollipop. So a tail, then a loop like this. Not that the only alphabet is A, so this is the possibility. And if you don't have this loop, the language must be finite, only finitely many strings. If the language is infinite, then you are guaranteed to get a loop, then definitely it looks like this. And some of the states may be final, right? So we are getting a Dfa, this is the generic structure of a Dfa. It doesn't matter which are final and which are non-final, but some of the states are final and some others are not final, right? Now given this, you can see that the length set is, if you look at this Dfa, what is the length set representing the language accepted by this Dfa? If you look at, you can see that this is the length set. Why? Because the initial state is final, null string is accepted whose length is 0. Now a cube is taking you to a final state, so the length of a cube is 3. 3 is also there. Then why is it that 5 is there? If you look at 1, 2, 3, 4, 5, 5 A's is taking you to a final state, so 5 is there. Now you can see that the loop length is 8. You are here now, then if you take 8 more A's, 1, 2, 3, 4, 5, 6, 7, 8, you are again accepting. So 5 plus 8 is 13. So definitely 13 plus 8, 21, plus 8, 29, plus 8, 37, plus 8, 45, plus 8, 53, plus 8, 61. Likewise, all those numbers are going to be in the length set. Then why is it that 8 is there? You can see, if you look at 8 is 1, 2, 3, 4, 5, 6, 7, 8, it is coming to a final state. So 8 is there as a length. Then definitely, because you are in a loop, after 8, if you process 8 more rays, you are again accepting. That is why 8 plus 8, 16 is there, plus 8, 24, plus 8, 32, plus 8, 40, 48, 56, 64, 72. Likewise it goes. So you can see that this is an ultimately periodic set. So if the single alphabet language is regular, we proved that then the length set is ultimately periodic. So the only if part is done. Now maybe we can look at the proof idea for the if part. For that, suppose A is an ultimately periodic set. You are just looking at an ultimately periodic set. For example, you take this as the ultimately periodic set. You have a finite prefix 0 to 5, and after 8, starting with 8, you have all the elements at a distance of 4. 8 plus 4 plus 4 plus 4, likewise it goes. So it is an ultimately periodic set. Now you can construct a DFA accepting strings over a single alphabet set language. Strings over a single alphabet set whose length set is exactly this. For example, I am giving you 1. I made this DFA in such a way that 0, the corresponding string is epsilon is accepted, then 2, a square is accepted, then 5, 1, 2, 3, 4, 5, a raised to 5 is accepted, then is 8, here is a raised to 5, 6, 7, 8 is accepted, then there is a loop of length 4. So 8, 12, 16, 20, 24, etc. it is accepted. So given an ultimately periodic set, then you can come up with a DFA accepting a language whose length set is the given ultimately periodic set. So if the set is ultimately periodic, then you can get a single alphabet set language such that it is a set of all a to the power m, such that m is in the ultimately periodic set given. So with this we are finishing this proof. So what we proved is that if you look at a single alphabet language, the language is regular if and only if its length set is ultimately periodic. Now we are going to generalize this for any regular language. May not be on a single alphabet set, can be on any alphabet set. We can see what we can do. As a corollary of the previous theorem, we can have this. Let L be a regular language over an arbitrary alphabet set sigma. Sigma may contain any number of alphabets, finitely many. May not. We are not just looking at a single alphabet in the set. It can be any number of alphabets. Then this set, what is it? The set of all string lengths. If x is in the language, you are looking at the number of symbols in x. That is this notation. That is the set of all lengths of the strings in the language is an ultimately periodic set. It is a very stronger result. So we are saying that if you look at any regular language or any alphabet set, then the length set is ultimately periodic. We need to have a proof. Here we will apply homomorphism that we discussed 2 lectures before. to have a proof for this corollary. Let L be a regular language over sigma. Sigma can be containing finitely many alphabets. Now you consider the homomorphic image of the language h of L, where the homomorphism is defined as follows: from sigma star, from strings over sigma to the singleton alphabet set 0. 0 is the only alphabet. So naturally, this is the definition of H, which is the homomorphism. For every alphabet in the alphabet set of the language, the homomorphic image of that alphabet is 0. So every alphabet will be replaced with the zeros. Example, if you look at strings over AB such that string length is even. For example, AB is in the language, BA is in the language, AB is in the language. A string is in the language if and only if its length is even, right? So what is the homomorphic image of that language? You can actually we have discussed it. You can see that it is nothing but 0 to the power 2n, where n is greater than or equal to 0. So even number of zeros, that is it. I hope you are getting it. Length set is the set of all even numbers here, because when you substitute different values of n, you can see it. So this is the set of all even numbers, the length set, and hence it is ultimately periodic. So for this for this example, we observe that the language is regular for sure, and its length set is ultimately periodic, and hence for this example it is okay. Now we have a single alphabet language h of L. Given an arbitrary language, a regular language over an arbitrary alphabet set, we are taking the homomorphic image where homomorphism is defined as h of any alphabet is 0, that the single alphabet. Then you can see that the homomorphic image of a language is regular, because from that lecture we know that homomorphic image of a regular language is regular. Now we have proved, because the homomorphic image preserves the length set. If you look at AB, then the homomorphic image is 0 raised to 4. The length is same. So when you apply this homomorphism, it is easy to verify that H and H of L will have the same length set. So the length set is preserved. So basically, from a language over an arbitrary alphabet set, we are getting a homomorphic image which is a single alphabet language, and the length set is same as the given language. And from the previous theorem, if we have a single alphabet language and the language is regular, then the length set must be ultimately periodic. So now by combining these two, we are proving that the length set of any regular language is ultimately periodic. So which is a very strong result. Let us see how we are going to apply this. From the corollary, we know that length set is ultimately periodic is a necessary condition for any language. Therefore, if we can prove that the length set of a given language L is not ultimately periodic, then we can conclude that L is non-regular, because for any regular language, the length set must be ultimately periodic, which is a necessary condition. So we can apply the ultimate periodicity result to prove that certain languages are non-regular. Look at an example. Here is a language which is a singleton alphabet language. What is it? A to the power n factorial. If the number of A's is a factorial, then it is in the language, otherwise not in the language. Just look at the length set, word set. This is 0 factorial or 1 factorial, 2 factorial, 3 factorial, 6 factorial, 7 factorial, likewise it goes. Sorry, this is 4 factorial, 5 factorial, 6 factorial, 7 factorial, likewise it goes. Now the question is it an ultimately periodic set? Is the length set? What do you think? See that the gap between the elements increases monotonically. Gap between these two is 1, between these two is 4, these two is 18, between these two is 96, then 600, likewise it goes on increasing. So the gap between successive elements keep on increasing, and hence we cannot find a period to catch every number in the sequence. So what is the period? If you want to start over here, it must be 96, but the 96 if you add to 120 you will never get 720. The gap keeps on increasing, so you will never find a period which can find or which can be added to get the next number. So you can conclude that this is not an ultimately periodic set. So this is not ultimately periodic since the gap is monotonically increasing. So language is non-regular. See how easily you applied it. If you observe that the length set is not ultimately periodic, no doubt then the language must not be regular. Length set is ultimately periodic is a necessary condition, but it is not a sufficient condition. Very important for a language to be regular. Meaning, by looking at the length set as ultimately periodic, it is wrong to conclude that language is regular. I will give you a counter example. See this language, set of all a to the power n, b to the power n, where n is greater than or equal to 0. If you look at the length set, it is the set of all even numbers, which is in fact an arithmetic progression and a periodic set. Starting from here, it is a periodic set with period 2. So it is an ultimately periodic set, but the language is not to be not regular. So this condition is not a sufficient condition. It is not sufficient to conclude that the language is regular, but it is necessary. If a given language is not satisfying this condition, if the length set is not ultimately periodic, then no doubt the language is non-regular. With this, we are coming to the end of this lecture, and I am giving you 2 exercise problems for you to practice and understand how the ultimate periodicity theorem can be used, or the corollary can be used to prove that certain languages are non-regular. Today we have seen a nice relationship between a regular language and its length set. We proved that for any regular language, the language can be over any alphabet set, the length set is ultimately periodic. So it is a necessary condition, and hence can be used to prove that certain languages are non-regular. So how we can prove? Just see what is the length set. If you can prove that the length set is not ultimately periodic, then you can conclude that the given language is non-regular. But it is not a sufficient condition. If you observe that the language having length set ultimately periodic, that it may not be correct to conclude that it is a regular language. We have seen counter example, that is A and Bn, whose length set is the set of all even numbers, which is periodic, but the language is known to be a non-regular language. Thank you.